For this final section, we're going to start with reasoning and sort of look into how that's different from problem solving. The next section will be decision making. Now these are all very similar because they're intertied processes that we do, but we're going to sort of separate each one and talk about them individually. So reasoning is a cognitive process, that we use to make inferences from knowledge and draw conclusions. So problem solving is like, how do we get from goal 1 to goal 2? Whereas reasoning fits into how do we know which knowledge is important and how do we draw conclusions about how to get to our end state. So reasoning is kind of in the middle. Reasoning also includes like doing logic, or sort of thinking through something. And a lot of reasoning is tied to stereotyping behaviors. So thinking that things are just like other things that you've seen. So we're going to do inductive and deductive reasoning, starting with inductive. So inductive reasoning is drawing an inference about something unknown. So something happens to us, and we are going to use specific instances to generalize to this unknown instance. So your friend says, hey, I want to go to Moe's. And you go, oh, what's a Moe's? I don't know what that is. And they say, oh, it's a burrito place. It's like Chipotle. So a specific instance to an unknown instance. There are several types of induction. So a general induction is when you generalize from known instances to every type. Okay, so it is like saying that you have this known instance that women are bad drivers, or that your friend Julie is a bad driver. So that means that all women are bad drivers. So going from one known instance to all instances, hence the general part. This is actually a type of classical conditioning or operant conditioning, so a generalization. So what they do to test that is play mastermind, which is a reasoning task that you can do as for an experiment. And so that research started in like the 1950s. Investigators devised a game very similar to mastermind. And what they did was that participants were given a bunch of cards, and there were rules about what cards were in the category and what cards were out of the category. But they weren't allowed to ask for the rules. They had to figure the rules out based on the way that the experimenter answered their questions. So the experimenters would vary these rules. So simple rules, things are all red, were easy. Conjunctive rules, like rules where they had to have two pieces, were harder. So it has to be red and a square. And even worse than that are disjunctive rules. Well, this or that. So we're good at simple rules, and as the rules get more complex, it tends to be a little harder. Negative rules, such things that were not red, which is really a disjunctive rule, blue or green or yellow or purple or orange. And disjunctive negative rules, such as not red or cross, which is really a very giant disjunctive positive equation, are the most difficult. And you'll see in some later sections that negatives tend to be extremely difficult for us to process, so negative rules that are very vague are hard. So this is an example of what the card task would look like. So I would have all these cards, and I would basically ask to sort them into categories, and I would say, is this in the category? And you would say no. So I would be able to use that feedback to determine what I should do next, essentially. That's general induction. A specific induction is when I have one instance to one other instance. Okay. So I'm not generalizing to all women. I would say maybe all women that are my friend's age and temperament. So I'm limiting my inductive range. That explains the typicality effect. So you'll say that similar members are part of this category because the things that they have are typical, versus saying that everything that looks like this is in that category. So the way to think about this is this specific induction is called the similarity coverage model. And coverage is the sort of correlation between two instances, especially like an exemplar for category comparison. And so I'm looking at how much they are similar. Things that are more similar get added to the category, so specific induction occurs. And things that are less similar don't get added, and that's when the specific induction does not occur. You say these things are different, so it doesn't count. Then the next section is deductive reasoning. So inductive reasoning is a specific induction and a generalized induction. Now on to deduction, deductive reasoning, which is studied a little bit more, although we do lots of inductive reasoning. So we're going to talk about syllogisms. Syllogisms are a way to study deductive reasoning. If you've had a basic logic class, this will be very familiar. And then what people do when they screw up reasoning. Right? So some errors in reasoning. So deductive reasoning is a way to understand rationality. Now humans are not rational, not in the least. Emotion gets in the way, lots of things. So ways to, we're really looking at how and when people are rational, which would explain the decisions they make. So lots of economic research is based on rationality and non-rationality, so descriptive and prescriptive models for what you are doing and what you should be doing. We'll cover that more in decision making, but reasoning is sort of part of that as well. So what people do is they use a syllogism. It's an argument that's two statements and a conclusion. Just give me an example. Oh, this slide's in the wrong place. So an example of some deductive reasoning. Fred is the brother of Mary. Mary is the mother of Lisa. So Fred is Lisa's uncle. That's a deductive process. A more inductive process would be that Fred is older than Lisa, because that's generally true. So we're going to talk about syllogisms now, finally. So it's an argument of two statements and a conclusion. So the first type, categorical, it examines the relationships between categories. So you say all poodles are pets, all pets have names, therefore all poodles have names. So all A are B, all B are C, therefore all C, A are C. And that's the pattern that this fits. So what you're supposed to do in this task is determine whether or not the conclusion can be drawn given those premises. So if I say all poodles are pets and all pets have names, can I say poodles all have names and that be true? In this instance, you're supposed to say yes, because this type of syllogism is true. So here's another couple of examples. So all Porsches are reliable. The Boxster is a Porsche, so the Boxster is reliable. Okay? If those things are true, then the conclusion is logically true. So all A are B, C is an A, therefore C is a B. And so you can make different types of syllogisms. So the universal affirmative is the one we just did. You can do universal negative, no A or B. And then you can sort of do partial affirmatives. So some A are B, right? And then you can determine how people interact, especially here of this particular affirmative. So what happens when that representation happens? So if I say some A or B, I could have which one of these four. And then a particular negative is basically the same thing in reverse. Some A or not B, so how do people represent that? So that's where we're really interested, not so much the top part. Alright, so the second type of syllogisms, conditional. So when the occurrence of an event is conditional on the occurrence of another, meaning these two things have to happen together, it's called a conditional syllogism. And generally those are written as if P then Q, or if A then B. Okay, so P is the antecedent, Q is the consequent. I think I have that on this slide. Okay, so the antecedent is the if condition, and the consequent is the result of the conditional, the then condition. So if we vary the antecedents and the consequence, what happened? All right. So there's 4 different ways that people can think about this. I can look for the antecedent. So if Porsche, then reliable. Okay. So I can check and make sure P is true. Now P is the Porsche part. So if Porsche, then reliable. Boxster is a Porsche, so it has to be reliable. So if P is true, Q is also true. I can do a denial of the antecedent if P is not true. Okay, so if Porsche, I have a Honda Fit, so not a Porsche, therefore I don't know if it's reliable. Okay. I can do affirmation of the consequent. I can look at when Q is true. So is something reliable? Well, my Fit is actually reliable, hopefully, fingers crossed. So if reliable, then Porsche. And you're not supposed to do that. People get in trouble for that part. Or I can do denial of the consequence, where I'm looking at where Q is not true. So my friend has a VW bus, not reliable at all, so therefore it's not a Porsche, because it's not. Okay. Which really leads us to 2 types of reasoning. Okay, so to do these sorts of logic tests accurately, you have to do modus ponens and modus tollins. So ponens is the rule of logic that if a conditional statement is true, so the whole thing is true if the antecedent is true, the consequent is true. So if I check and make sure A is true and then B is true, I go to check. Okay, so the way to think about this is if it's raining, then I need my umbrella. Okay, so it's raining outside, so I need my umbrella. So I've checked A, or Q if P. So if raining, then umbrella. Umbrella, check, it's true. People are good at this part. Tollins, a little harder. So the rule of logic is that the conditional is true if the consequent is false. So this is denial of the consequent, which is the Q part, or B in this example. So this would be if I don't have my umbrella, then it's not raining. So no umbrella, no rain. Okay. What people want to do is affirmation of the consequent. If umbrella, then rain. Well, I carried my umbrella today, but it didn't rain. So what you want to think about when you have these sorts of problems, if P then Q, that does not mean if Q then P. That's what people want to have happen. So you can't affirm the consequent. That doesn't mean anything the way these are set up. That's what people want to have happen. So another example about rain, because that helps. If the grass is wet, then it rained. Okay. So if wet, then rain. Okay, the grass is wet, it rained. But you can't affirm the consequent. If rain, then the grass is wet. Okay, that's a terrible example actually, but you get the idea where you can't say if the consequent is true, then the whole thing is true. I should have done it the other way. If it's raining, the grass is wet. Okay, that makes more sense. So I check if it's raining, yes, then the grass is going to be wet. However, I could say if the grass is wet, then it's raining. Well, the grass could be wet because the sprinklers are on. So I can't affirm the consequent. Sorry, I said that backwards. So what this leads us to is the Wason selection task. This is another experiment that you'll get to take. And so the rule that they give people is if there's a vowel on one side, then there's an even number on the other side. So I have to check all these cards to determine how I can check and see if that rule is true. Okay. So if I give you if, vowel, then number. So which ones would you pick? Well, the easiest one to start with is E, because that's a vowel. I've got to flip that card over and make sure it's a an even number on the back. What happens next is people want to pick 4, because if it's an even number, it needs to be a vowel. But I don't have any rules about if even. So what you're actually supposed to pick is 7. If there's an odd number, I've got to deny the consequent or disconfirm the consequent. If it's an odd number and it's got a vowel on the back, I'm doing something wrong. So 90% choose E. You're supposed to pick that one. 60% choose 4, but you're not supposed to pick that one. Only 25% check the other one they're supposed to, and 15% actually choose the one that has nothing to do with anything. Okay? So when are we good at this task, at this sort of reasoning? Okay. If you make the material meaningful, people are better at it. So if a person's drinking beer, they're over 19, so we make the rule something a little unfamiliar. So if you're a cop, who do you check? Well, clearly you check the people drinking beer because they've got to be legal. Right? Do you check the people drinking Coke? Nah, don't care. Right? Do I check the 19-year-old? Nope, don't care, because if I already know they're legal. But I check the 16-year-old because that's the disconfirming the consequent to make sure that they're drinking Coke still. Okay, so we're better when it's more meaningful. Alright, so I'm going to end this on a great note about why we're terrible at reasoning, which kind of sucks because this whole section is things that we're bad at. So people will be poor at a syllogism task when there's a form error. So form errors occur when you will accept a conclusion as true if the same quantifiers appear, some, all, or none, throughout the other pieces of the syllogism. So there's 2 types. First type is called the atmosphere effect, and that happens when the way that the first 2 pieces are worded, all A or B, all B or C, creates this sort of mood, this atmosphere, that leads people to accept a conclusion even containing the same terms, even though it's not correct. Okay. So I could say some women are lawyers. Yeah. Some lawyers are men. Also true. Therefore, some women are men. Ooh, not true, right? Generally. So the idea is that I could say some women are some A or B, some B or C, therefore some A or C. That sounds reasonable. Yeah, it makes sense. But not when you plug in this type of wording. The second type of form error is called matching bias. And the difference between atmosphere effect and matching bias is that atmosphere effect is about the mood of the equation, if you will, whereas matching bias is always about the syntax. It's about the actual order of the words. So we'll accept a conclusion as valid if it has the same syntax. They're very similar. The atmosphere effect is more about it's saying some, and some, whereas matching bias is more about the grammatical syntax. Alright, second type of error is called a content error. And this is belief bias. So we've talked a little bit about this before. It's the tendency to think that things are believable. You're going to accept those as true over unbelievable ones. Because there's just sort of this yeah, well, that's the way the world works, so it must be true. So we're going to agree with the syllogism even if it's not true, just because it sounds like it's true. And you see this on the internet all the time, right? So people post things on your Facebook page that you're like, really, how can you believe that's true? Well, it sort of sounds true, so it must be true, right? Because it's printed on the internet. That's a belief bias effect. So, example, all lawyers are human, we think. All Republicans are human, therefore some lawyers are Republicans. Well, the conclusion is perfectly believable because that is actually true about the way the world works. But if you're looking at logic-wise, we have all A are B, all C are B, therefore some A are C. Okay, so you're supposed to say no because you really should say, given these antecedents, the consequence should be, therefore, all lawyers are Republicans, would be true. And you would actually know to that one, you would be bad at that task too, because we know that that's false in the real world. So why do we do this? The idea behind deductive reasoning is that the deduction depends on sort of these mathematical principles that we have in our head. So we construct a mental model of the world and try and verify that with proof from our long-term memory that we've pulled into working memory. So we have this picture of what's going on, we pull up the picture that we know is true, we try to make a match. Okay, which we've already talked about being bad. So reasoning is something that we actually are pretty terrible at because we're so prone to these different biases. I know that the syllogism tests are a little weird, but they help us understand, again, when things break, and that gets at really like, when are people good at tasks and when are people bad at tasks? Well, if we can find out when they're bad, that sort of explains when they're good.